Hello and welcome. Get comfortable and allow yourself to relax. In this gentle journey, we will explore some fundamental ideas of introductory organic chemistry in a calm, soothing narrative. As you listen, you can let go of any stress or worry. We'll wander through the world of molecules at a slow, sleepy pace, touching on the nature of alcohols, how they form and change, the characteristics of carboxylic acids and their relatives, the magic of Grignard reactions, and even the soft signals of NMR spectroscopy. There's nothing to do and nowhere to be. Just listen softly as we describe these chemistry concepts like a bedtime story. Take a slow breath, settle in, and let's begin our peaceful exploration of organic chemistry together. We begin with the alcohols, a family of organic compounds that contain the hydroxyl group, OH. Alcohols are very common and useful. They appear throughout nature, in industry and around the house. If you've smelled the sweetness of ripe fruit or used hand sanitizer, you've encountered alcohols. The simple alcohol ethanol is found in alcoholic beverages and also used as a solvent and fuel. Another example is isopropanol, also known as rubbing alcohol, often used as a disinfectant. These familiar liquids are part of the same chemical family, defined by that OH group. In an alcohol molecule, a hydrogen H and oxygen O pair together as a hydroxyl group attached to a carbon framework. This OH group is like a little polar handle on the molecule, making the alcohol special in how it behaves and interacts. Let's picture an alcohol molecule in our mind's eye. Imagine a chain of carbon atoms, and on one of them is a hydroxyl, an oxygen and hydrogen bonded together, hanging off the carbon like a tiny hook. That OH group is what makes the molecule an alcohol. It also makes the molecule polar, meaning one end, the OH end, has a slight negative charge on the oxygen and a slight positive charge on the hydrogen. Because of this polarity, alcohol molecules can form hydrogen bonds with each other, a gentle attraction where the partially positive hydrogen of one OH is drawn to the partially negative oxygen of another. These hydrogen bonds are quite weak individually, but collectively they create a significant attraction. As a result, alcohols tend to stick together more than similar molecules that lack an OH, leading to high boiling points and strong intermolecular interactions. For example, compare an alcohol like ethanol to an alkane like ethane, which has no OH. Ethanol boils at 78 degrees Celsius, whereas ethane boils at a chilly 89 degrees Celsius. The alcohol's hydrogen bonding allows it to stay liquid until a much higher temperature because extra energy, heat, is needed to separate those strongly attracted molecules. In the same way, small alcohols are quite soluble in water. They mix readily because they can hydrogen bond with water molecules too. Water welcomes the alcohol by holding onto its OH group. However, as the carbon chain of an alcohol grows longer, its character becomes more like an oil, hydrocarbon-like, and it doesn't mix as well with water. The larger, oily part resists the water, and the alcohol becomes less soluble. For instance, methanol, 1 carbon, and ethanol, 2 carbons, mix completely with water, but an 8-carbon alcohol, octanol, is practically insoluble in water. The balance between the hydrophilic water-loving OH and the hydrophobic water-fearing carbon chain shifts as the molecule gets larger. Alcohols are not only common, they're also quite useful as solvents. Because they have both a polar part, the OH, and a non-polar part, the carbon chain, they can dissolve a wide range of substances. Ethanol in particular is often called a green solvent in chemistry. It's relatively non-toxic, comes from renewable sources like fermentation of grains or fruits, and is safe for the environment compared to many other solvents. In fact, aside from water, ethanol may be the most environmentally friendly solvent commonly used in organic chemistry. If you swirl a bit of ethanol in a flask of organic material, it's gentle yet effective at helping reactions along or extracting compounds, all while being easy to remove later by simple evaporation. Now, let's classify the different types of alcohols. Not all alcohols are alike. Some are considered primary, some secondary, and some tertiary. This classification refers to how many other carbons are bonded to the particular carbon that carries the OH group. In a primary alcohol, the carbon bearing the OH, sometimes called the carbonyl carbon, is attached to only one other carbon, or none in the case of methanol. If that carbon is bonded to 2 other carbons, the alcohol is secondary. If 3, it's tertiary. For example, consider propanol. 1-propanol, CH through CH2 to OH, is a primary alcohol because the OH is on an end carbon attached to just one neighbour carbon. 2-propanol, isopropanol, CH3-2HEOH, is a secondary alcohol. Its OH-bearing carbon is connected to two other carbons, the two CH3 groups. If we had an alcohol where the OH-bearing carbon was connected to three other carbons, imagine something like CH3COH, tert-butyl alcohol, that would be a tertiary alcohol. This classification matters because it influences the alcohols. More on that later when we talk about oxidation. There's also a special class of alcohols called phenols. A phenol is what we call it when a hydroxyl group is directly attached to an aromatic benzene ring. Phenols have some unique properties due to the aromatic ring, particularly in terms of acidity, but structurally you can think of them as aromatic alcohols. If you imagine a benzene ring, a hexagon of carbon atoms with a pleasant aromatic stability, and see an OH connected to it, that's a phenol. Phenol itself, C/H/OH, is a distinct compound, a disinfectant in older times, and many natural molecules like the flavour vanillin or the pigment in berries have phenolic OH groups on aromatic rings. Now let's gently discuss how we name alcohols, their nomenclature, but we'll do it softly without any rush. In the IUPAC naming system, which is the formal way chemists name compounds, an alcohol's name is based on the longest carbon chain that includes the OH group. We take the name of the corresponding alkane, the chain of carbons, drop the final -E of that alkane name, and add L to signify it's an alcohol. Also, we give the carbon with the nice OH the lowest possible number in the chain numbering. For example, ethane, a 2-carbon alkane, becomes ethanol when it has an OH, and indeed ethanol is CH3 minus CH2 minus OH. For a slightly longer example, CH3CH2CH2OH, 3 carbons with an OH on the end, would be named propan-1-ol, often just called 1-propanol, indicating the OH is on the first carbon. If the OH were on the middle carbon of a 3-carbon chain, CH3 minus COH minus CH3, we'd call it propan-2-ol, 2-propanol, since the OH is on the second carbon. We also include any other substituents in the name as prefixes, just as with other compounds, and we always ensure the OH's carbon gets the lowest number to properly emphasize the alcohol functionality. If there's a ring, like a cyclic alcohol, by convention, the carbon bearing the OH is position 1 on the ring, so we don't need to number the OH in a simple cyclic alcohol. For instance, cyclohexanol means a cyclohexane ring with an OH at carbon 1. And if that OH is on a benzene ring, as mentioned, we call the compound a phenol. The parent name phenol is used for benzene with OH. Sometimes we encounter alcohols with 2 hydroxyl groups. These are called diols or glycols. In naming diols, we keep the nice E of the alkane name and add diol. For example, HOOCH2CH2OH is ethane 1-2 diol, commonly known as ethylene glycol, with 1,2 diol indicating OH groups on the first and second carbons. We would provide numbers for both hydroxyl locations like 1,2 or 1,3 in the name as needed. There are also common names for some alcohols like isopropyl alcohol for 2-propanol or glycerol for propane 1,2,3-triol, but in our dreamy journey, we won't dwell on those too much. Just know that the systematic way to name an alcohol is with that mas-ol ending, guiding us to recognize the presence of a hydroxyl group. Now that we have an idea of what alcohols are and what we call them, let's talk about some of their properties in a gentle way. We already mentioned that alcohols are polar molecules and can form hydrogen bonds, which gives them higher boiling points compared to similar-sized non-alcohol molecules. Picture a group of alcohol molecules holding hands through hydrogen bonds. It takes a lot of heat to make them let go of each other and fly off as gas, hence the higher boiling point. We also noted that small alcohols mix well with water, essentially because they can handshake, hydrogen bond with water molecules themselves. A little alcohol like methanol or ethanol will dissolve in water easily. However, as the alcohol's carbon chain gets longer and greasier, it begins to resist mixing with water. The non-polar part of the molecule starts to dominate its behavior. So solubility in water decreases as the carbon chain length increases. Still, even larger alcohols might dissolve a bit in water, and water can dissolve a bit in them due to that OH group trying to reach out and grab onto water molecules. Chemically, an alcohol's behavior is influenced by the oxygen's lone pairs and the polarity of OH. Alcohols are weakly acidic. The OH bond can donate a hydrogen H mass to strong bases, but it's not nearly as eager to do so as a true acid like HCl. In fact, the typical pKa of a simple alcohol is around 16 to 18, very close to the pKa of water, 15.7. That means in pure water, an alcohol barely dissociates at all. Only a tiny fraction of OH groups lose their proton. To deprotonate an alcohol completely and form an alkoxide, the OH ion, one usually needs a strong base, much stronger than the hydroxide in NaOH. Bases like sodium hydride, NaH, or sodium metal, which generates Na-ionomers by stripping the proton and releasing H2 gas, are used to make alkoxides. For instance, if we add solid NaH to ethanol, it will deprotonate the ethanol to give sodium ethoxide, CH3CH2O amides, and hydrogen gas bubbling out. This shows that alcohols are very weak acids, giving up H by only to very strong bases. On the flip side, alcohols can also act as weak bases. The oxygen atom has lone pairs that can accept a proton from a strong acid. If you drop an alcohol into strongly acidic conditions, say concentrated HCl or H2S4, the oxygen can pick up an H bias and become protonated, turning OH into OH2 bias, an oxonium ion. In that state, the alcohol becomes a much better leaving group, which is useful in certain reactions. But under normal conditions, neutral pH, an alcohol doesn't carry a charge and mostly just behaves as a neutral polar compound. It's comforting to remember that alcohols are not reactive extremes. They are not very acidic, not very basic, but they can gently participate in reactions when coaxed by the right conditions. Now that we've been introduced to alcohols and their nature, let's float onwards to see how we can create alcohols and how they can be transformed. In organic chemistry, making an alcohol, MnIOH, can be done in several ways, like different paths leading to the same cozy cabin. One straightforward way is to perform a substitution reaction on an alkyl halide. This means if we have a molecule with a leaving group like bromine or chlorine attached to a carbon, an alkyl halide, we can replace that leaving group with a nice OH by treating it with a hydroxide source. For example, if you have bromoethane, CH3CH2-Br, and you treat it with sodium hydroxide, the SOH can do an SN2 nucleophilic substitution, kicking out the bromide and taking its place, yielding ethanol CH3CH2-NOH. So alkyl halide plus OH minus alcohol is one method, particularly good for primary alkyl halides. Another route is by adding water to a double bond known as hydration of an alkene. Alkenes, carbon-carbon double bonds, can react with water HOH in the presence of an acid catalyst. The water adds across the double bond. One carbon gets an H, the other gets an OH, converting the double bond into a single bond and yielding an alcohol. For instance, if we take ethylene, CH2 equals CH2, and add water with a little acid to catalyze, we get ethanol, CH3CH2OH. In fact, billions of gallons of ethanol are made industrially by this exact acid-catalyzed hydration of ethylene. It's like adding a drop of water across the double bond's pi bond. These two approaches, substitution on alkyl halides and alkene hydration, are classical ways to make alcohols and might be among the first reactions you learn in organic chemistry. Beyond those, there are more powerful methods to create alcohols, especially when we want to do it in a more controlled or specific way. One very important approach is by reducing carbonyl compounds. Carbonyl refers to the C equals O group as found in aldehydes, CHO, and ketone, and COR. If you have an aldehyde or ketone, you can add hydrogen across the C equals O double bond, effectively turning C equals O into COH, while also adding a hydrogen to the carbon. This is chemically in reduction, adding equivalent of H2 to the molecule, and it yields an alcohol. For instance, reducing an aldehyde gives a primary alcohol, and reducing a ketone gives a secondary alcohol. How can we do this reduction gently? One way is catalytic hydrogenation using H2 gas with a metal catalyst, but that method is often too unselective. It might also reduce other unsaturated parts of the molecule, like double bonds. Instead, organic chemists typically use hydride-reducing agents. These are reagents that deliver an H hydride ion, which is like a proton with 2 electrons, to the carbonyl carbon. Two commonly used reducing agents are sodium borohydride, NaBH4, and lithium aluminum hydride, LiAlH4. Think of them as sources of a hydrogen in the hand that can attack the positively polarized carbon of a C equals O. Sodium borohydride is the gentler one. It will readily donate hydride to aldehydes and ketones, converting them into alcohols. It's often used in alcoholic or aqueous solvents and is mild enough that it generally won't touch esters or carboxylic acids, which have less reactive carbonyls. Lithium aluminum hydride, on the other hand, is much stronger, a far more reactive source of hydride. It can reduce virtually any carbonyl-containing functional group. Aldehydes, ketones, esters, and even carboxylic acids all will succumb to LiLH and be reduced to alcohols. LiLH is so reactive it must be used in aprotic solvents, often ether, and water must be added only after the reaction to protonate the oxygen. Otherwise, LiLH would react violently with water itself. So the typical gentle procedure is add NaBH to a solution of an aldehyde or ketone, and it will quietly yield the corresponding alcohol after a little while. Or, for a carboxylic acid or ester, use LiLH carefully, dropwise, in an ether solvent. Then after it's done its job adding H-months, add some water to release the alkoxide to a neutral alcohol. For example, if you reduce acetone, a ketone, with NaBH4, you get isopropanol, 2-propanol, a secondary alcohol. If you reduce acetic acid, a carboxylic acid, with LiLH4, you'll get ethanol, a prialcohol. Reduction is like giving the molecule a comforting hug of hydrogen. In summary, hydride reagents add a hydride ion to the carbonyl carbon, turning C equals O into an alkoxide, CO-, which upon protonation becomes COH. A new alcohol has been formed. It's a very common way to prepare alcohols in the lab, especially for synthesizing specific structures. There's another particularly magical method to create alcohols, one that also builds new carbon-carbon bonds in the process, and that is through Grignard reactions. A Grignard reagent is a special kind of organometallic compound, basically an alkyl magnesium halide, formula RMgX, where X is typically bromide or iodide. To make a Grignard reagent, we take an alkyl halide, say RBr, and add it to metallic magnesium shavings, usually in an ether solvent. The magnesium inserts itself into the RX bond, yielding RMgX. This transforms the carbon from being attached to a relatively electronegative atom, Br, to being attached to an electropositive metal, Mg. The carbon atom in RMgX becomes electron-rich, almost carbanion-like. In fact, we can think of RMgX as if it were R-ment a carbanion paired with MgX-mise, although it's more complex in reality. The important thing is that the R group, which could be a methyl, an alkyl, etc., in a Grignard reagent, is a strong nucleophile and a strong base. It is eager to attack electrophilic centers, particularly the carbonyl carbon in aldehydes, ketones, and other carbonyl-containing compounds. When a Grignard reagent attacks a carbonyl, it forms a new carbon-carbon bond, adding the R to the carbonyl carbon and pushing electrons up onto the oxygen, forming an alkoxide. Then, when water or a mild acid is added in a separate step called workup, that alkoxide is protonated to give an alcohol. The beauty here is that you not only made an alcohol, you also connected two carbon frameworks, so it's a powerful way to build more complex molecules from simpler ones. Let's imagine this stepwise. We prepare a Grignard reagent from, say, ethyl bromide, CH3CH2-Br, with magnesium, yielding ethyl magnesium bromide, CH3CH2, known as MgBr. Now we have a nucleophilic ethyl unit, basically CH3CH2 nalus in character, ready to attack. If we add this to formaldehyde, H2C equals O, the simplest aldehyde, the ethyl carbanion will attack the carbonyl carbon, attaching CH3CH2s to it and turning the C equals O into CO nursing. After adding a bit of water to protonate, we end up with ethanol, CH3CH2OH, a primary alcohol. In general, Grignard addition to formaldehyde yields a primary alcohol. If instead we add the ethyl Grignard to an aldehyde like acetaldehyde CHCHO, the ethyl attaches to the carbonyl carbon, which already has one methyl attached, and after protonation we get a secondary alcohol, in this case 2-butanol, CH3CHOH CH2CH3. So Grignard addition to an aldehyde produces a secondary alcohol. Now if we take a ketone such as acetone CH3CH3 and add our ethyl Grignard, the ethyl attaches to the carbonyl, which has two other carbons attached already, and upon workup we get a tertiary alcohol, in this case 2-methyl-2-butanol, CH3COH CH2CH3. So Grignard addition to a ketone yields a tertiary alcohol. We can see a pattern. The type of alcohol formed, 1 degrees, 2 degrees, corresponds to whether the Grignard was added to a formaldehyde, no prior carbon substituents on C equals O, giving an aldehyde, 1 substituent on C equals O, giving 2 degrees, or a ketone, 2 substituents giving 3 degrees. Each time, a beautiful new CC bond is forged in the process. Grignard reagents can do even more. If you react a Grignard reagent with compounds like esters or acid chlorides, something interesting happens. The Grignard can add twice. The first addition to an ester will kick off the leaving group, OR, and form a ketone intermediate, and then a second mole of Grignard will add to that newly formed ketone, resulting overall in addition of 2 R groups to the original ester and yielding a tertiary alcohol after protonation. For example, adding excess CH3 MgBr to ethyl acetate, an ester, would ultimately give 2-butanol after workup, 2 methyls added to the original acetyl group. In practical terms, one usually plans to use 2 equivalents of Grignard for each ester or acid chloride, ensuring that there is enough to perform both additions. It's like the Grignard reagent says, I see a carbonyl, I'll add. Oh, now there's another carbonyl, after the first addition made a ketone, I'll add again. And it does, resulting in a heavily substituted alcohol. This is a powerful way to construct complex alcohols that have multiple carbon groups attached. Now, a gentle word of caution about Grignard reagents. Because they act like carbanions, which are extremely strong bases, they are very sensitive to water or anything acidic. If a Grignard reagent encounters water, it will simply grab a proton to form a hydrocarbon and be destroyed. For instance, CH3CH2 MgBr plus H2O would just give CH3CH3 ethane and MgBrOH. Therefore, when working with Grignard reagents, chemists take care to use anhydrous, water-free conditions, typically using dry ether solvents and glassware that has been dried. The ether solvent, like diethyl ether or THF, also helps stabilize the Grignard reagent, coordinating to the magnesium and keeping it happy in solution. So you can imagine the lab setup, a flask with magnesium and alkyl halide in ether, all under an inert atmosphere, producing this magical Grignard solution that must not see a single drop of water. It's quite dramatic, but in our calm story we just remember, keep the Grignard reagent cozy and dry. One especially interesting reaction of Grignard reagents is with the simplest carbonyl of all, carbon dioxide, CO2. CO2 can be seen as O equals C equals O, with a carbon in the middle that is electrophilic. If you bubble C from dry ice, for example, into a Grignard solution, the RMgBr will add to the carbon of CO2, effectively inserting itself and turning CO2 into a carboxylate, no COO miles attached to R. After adding acid in workup, this yields a carboxylic acid, R thus COOH. So a Grignard's carbon dioxide followed by water gives a carboxylic acid. This is actually a 2-step way to convert, say, an alkyl bromide into a carboxylic acid with 1 more carbon. It's like pulling CO2 out of thin air and sticking it onto the organic chain. For example, if we take methyl magnesium bromide, CH3 minus MgBr, and react it with CO2, then add acid, we get acetic acid, CH3COH. It's a straightforward yet fascinating route in synthesis. At this point in our journey, we have learned how to create alcohols either by adding hydride to carbonyls or by adding organomagnesium, Grignard reagents to carbonyls. The next gentle step is to see the other side of the coin. How can alcohols be transformed by oxidation? Oxidation is essentially the opposite of reduction. For a carbon atom, oxidation often means removing H2, or adding oxygen, so that the carbon forms more bonds to oxygen or fewer to hydrogen. We recall that a primary alcohol, RCHOH, has 2 hydrogens on the carbon bearing the OH. If we remove 1 hydrogen, the one from the OH, and another hydrogen from that carbon, we form a double bond to oxygen, C equals O, yielding an aldehyde. That is the first step of oxidizing a primary alcohol. If we oxidize further, essentially adding an oxygen or removing another H2, the aldehyde RCHO can become a carboxylic acid, RrCOOH. So in summary, a primary alcohol can oxidize to an aldehyde if carefully controlled, and then to a carboxylic acid under strong or prolonged oxidation. A secondary alcohol, RCHROH, has only 1 hydrogen on the OH-bearing carbon. Removing that H and the OH's hydrogen forms a C equals O, giving a ketone. And a tertiary alcohol, RCOHRR, has no hydrogen on the carbon with the OH. As a result, it generally cannot be oxidized at all under normal conditions. Oxidation usually requires that there's a hydrogen to remove. A tertiary alcohol lacking this hydrogen is resistant and doesn't form a carbonyl. If one were to somehow oxidize a tertiary alcohol harshly, it would break bonds and fragment the molecule rather than neatly form a C=O. So you can think 1 degrees alcohol, aldehyde, acid, 2 degrees alcohol, ketone, 3 degrees alcohol, no reaction, no easy oxidation. In practice, chemists have developed many reagents to carry out these oxidations, each with a different strength. Strong oxidizers like chromic acid, H2FeRO4, or other chromium Vi reagents such as sodium dichromate, CrO3 in acid, etc., will typically push a primary alcohol all the way to a carboxylic acid. If you treat ethanol with, say, chromic acid, it will first form acetaldehyde and then quickly further oxidize to acetic acid. On the other hand, milder oxidizers can stop the process at the aldehyde stage for primary alcohols. A classic milder agent is PCC, pyridinium chlorochromate, which in an anhydrous solvent will oxidize a primary alcohol to an aldehyde and not go further to the acid. Because it lacks water, it can't hydrate the aldehyde to then oxidize it more. Other non-chromium-based oxidants like the Swern oxidation, using DMSO and oxalyl chloride, or the Des-Martin periodinane are also gentle, producing aldehydes from primary alcohols without overshooting to acids. But if an aldehyde is left in the presence of strong oxidants, especially in water, it will hydrate and then oxidize to the acid. Secondary alcohols are simpler. Both strong and mild oxidants will convert them just to ketones, and ketones generally resist further oxidation unless extremely harsh conditions are used, breaking carbon-carbon bonds. And as noted, tertiary alcohols are generally non-oxidizable under these reagents. If you try, nothing happens, or the molecule might degrade in a complex way because you can't form a stable carbonyl by removing a hydrogen that isn't there. You might wonder why a tertiary alcohol can't be oxidized to something like a tertiary carbocation. Also, the issue is for a carbon to form a double bond to oxygen, it must lose the hydrogen that was attached to it. With no such hydrogen, a strong oxidizer might instead break a carbon-carbon bond, which is not a clean or useful reaction in most cases. So chemists usually say tertiary alcohols don't oxidize in the normal sense. Let's imagine this in a friendly way. If an alcohol is a little house with some hydrogen attachments, then oxidation is like gently removing some of those attachments and allowing the house to form a double-bonded extension, a carbonyl. A primary house has 2 attachments, H's, to remove, so it can extend twice to aldehyde, then to acid. A secondary house has 1 attachment, 1 H to remove, so it extends once to ketone. A tertiary house has none, so it stays as it is. You can't extend it without breaking the house apart. Knowing this, chemists choose the right reagent as a tool depending on what they want. If we want to stop at the aldehyde stage, we choose a mild tool that will carefully remove just 1 hydrogen. If we want to go to the acid, we use a stronger tool that will remove 2. And for secondary alcohols, any tool will do since it's just 1 step to ketone. With that understanding, we drift onward to carboxylic acids, which we've already touched upon as the oxidation product of primary alcohols. Carboxylic acids are characterized by the COOH functional group, also written as (C=OH). This group is called a carboxyl group, and it's like having a carbonyl C=O and a hydroxyl OH on the same carbon. Carboxylic acids are prevalent in nature. For example, acetic acid, ethanoic acid, gives vinegar its smell and acidity, and citric acid with 3 carboxyl groups makes lemon sour. These acids are fundamental in biochemistry and organic chemistry. In our course context, carboxylic acids and their derivatives form a big family. First, focusing on the acids themselves. A carboxylic acid is indeed an acid, though a relatively weak one compared to strong mineral acids. Typically, the pKa of a carboxylic acid is around 4 to 5, meaning they dissociate partially in water to give a carboxylate anion, minus COO members, and a proton, H. For example, acetic acid has a pKa of Car-4-8. That's much lower, more acidic than an alcohol's pK of 16, indicating carboxylic acids are far stronger acids than alcohols. However, compared to a strong acid like HCl pKa 7, carboxylic acids are still weak. They don't completely dissociate in water. Why are carboxylic acids more acidic than regular alcohols? The secret lies in the stability of their conjugate base, the carboxylate anion. When a carboxylic acid, RCOHA, loses a proton, it forms RCOM, which can resonate. The negative charge is not stuck on one oxygen, but is delocalized over both oxygen atoms through resonance. In other words, the carboxylate ion is a symmetrical blend of two structures, one with the charge on the first oxygen, one with it on the second. This delocalization stabilizes the anion. By contrast, if an alcohol loses a proton, you get an alkoxide arome, where the negative charge is localized entirely on one oxygen, no way to spread it out over multiple atoms. So, the carboxylate is inherently more stable, lower in energy, than an alkoxide, and that stability makes it easier for the acid to form, hence the acid is stronger. We can softly say carboxylic acids are weak acids, but still much stronger than alcohols due to the resonance stabilization of the carboxylate ion. Additionally, electron-withdrawing substituents like a chlorine on a nearby carbon can further increase a carboxylic acid strength by inductively pulling electron density away from the carboxylate, stabilizing the negative charge even more. Conversely, electron-donating groups make them slightly weaker. But all carboxylic acids share that resonant anion feature. Physically, carboxylic acids have notable properties. They are usually highly polar and can engage in extensive hydrogen bonding, even more so than alcohols. In fact, two carboxylic acid molecules often form a special kind of pair called a dimer. They hydrogen bond to each other in a cyclic fashion, each molecule donating one hydrogen bond and accepting one, making a sort of ring of two molecules held together by two hydrogen bonds. This strong pairing means that in the liquid or solid state, carboxylic acid molecules are quite stuck to each other. Hence, they tend to have even higher boiling points and often melting points than comparable alcohols. They also tend to be reasonably soluble in water, at least for the smaller ones, because they can both donate and accept hydrogen bonds with water molecules. For example, formic acid and acetic acid mix with water easily. Even benzoic acid with a large aromatic ring has limited solubility in hot water because of the COOH group's polarity. If you recall the smell of vinegar, acetic acid, or butyric acid, the odour of rancid butter, you might also notice these acids often have strong, pungent odours. In water, a carboxylic acid will partially dissociate to carboxylate an H3O base, which is why aqueous solutions of them are typically mildly acidic. Vinegar is 5% acetic acid and its pH is around 2 to 3. Now, nomenclature for carboxylic acids is straightforward in IUPAC. We find the longest chain that includes the carboxyl group and name the molecule with the suffix -oic acid. For example, CH3COOH is ethanoic acid, common name acetic acid. HCOOH is methanoic acid, common name formic acid, and so on. If we have a carboxylate anion, the deprotonated form, we use the suffix -ot for the anion name. So acetic acid becomes acetate when it loses H pites. Benzoic acid becomes benzoate, etc. You might have heard of sodium benzoate, a food preservative, or sodium acetate. Those are just the salts of the corresponding acids. In our minds, we can see a carboxylic acid is like a hand with two fingers, O and OH, that can either hold a hydrogen in the acid form or release it and hold a metal cation by electrostatic attraction in the salt form. For instance, sodium acetate is the acetate ion holding onto an Na pimes instead of an H. How do we prepare carboxylic acids? We've already mentioned a couple of ways. Oxidizing a primary alcohol or even an aldehyde will yield a carboxylic acid. In an earlier part of our story, we also talked about how adding a Grignard reagent to CO2 gives a carboxylic acid after protonation. Another common method is the hydrolysis of nitriles, cyanides. A nitrile, RCN, can be thought of as a hidden carboxylic acid. If you add water with acid or base and heat to a nitrile, it will break the CN triple bond and form a carboxylic acid, converting CN into COOH. For example, if you take ethane nitrile, acetonitrile, CH3CN and hydrolyze it, you get acetic acid, CH3COOH. This is a useful two-step sequence. You can convert an alkyl halide to a nitrile via SN2 with cyanide, then hydrolyze the nitrile to an acid, effectively lengthening the carbon chain by 1 and ending up with a carboxylic acid. This method and the Grignard CO2 method both allow one to start from something like an alkyl bromide and end up with a carboxylic acid that has one extra carbon. Mother Nature also has ways. Oxidation of an alkyl benzene at the benzylic position yields benzoic acid if there's at least one benzylic hydrogen. And oxidative cleavage of alkynes, triple bonds, can produce carboxylic acids if you break the triple bond with strong oxidizers. But softly speaking, the main laboratory preparations to keep in mind are primary alcohol or aldehyde oxidation, nitrile hydrolysis, and Grignard carboxylation. Carboxylic acids, being acids, undergo typical acid-base reactions. They form salts with bases, for example. If you add sodium hydroxide to acetic acid, you get sodium acetate. The acid is neutralized, and you get water and a carboxylate salt. This can be a convenient way to separate acids from other compounds, since the salts are often water-soluble, while the neutral acids might not be. Many carboxylic acids exist in biological systems in their deprotonated form, like citrate, lactate, fatty acid salts, etc., because the physiological pH is around 7.4, above the pKa of many acids, so they stay deprotonated. Now, carboxylic acids have a whole family of derivatives, which are like different costumes the carboxyl group can wear. We use the term carboxylic acid derivatives for compounds that, in a sense, can be converted to carboxylic acids by simple reactions like water addition, hydrolysis. These derivatives include acid halides, acyl chlorides, RCl for example, acid anhydrides, RCOOCOR, esters, RCOR, amides, RNH2 or ArcoHR, and nitriles, RCN, is often included in this family as well. In each of these, the carbonyl carbon is bonded to an electronegative atom or group, in place of the OH that a carboxylic acid has. In acid chlorides, it's bonded to a chlorine, in esters to an OR group, in amides to a nitrogen, in anhydrides to another carbonyl group through an oxygen bridge. If you look at a carboxylic acid derivative, the carbonyl carbon typically has 3 bonds to electronegative atoms, counting the double bond to oxygen as 2 bonds effectively, and the single bond to, say, Cl or O as another. This is the same oxidation state as the carboxylic acid itself. We can imagine that each derivative is, at least hypothetically, formed from a carboxylic acid by a condensation reaction, losing a small molecule. For example, an acid chloride can be thought of as a carboxylic acid that lost H2OH and gained Cl, essentially RCOOH plus 2RCOCl, losing H2O and SO2, it's like HCl byproducts. An anhydride is like 2 acids joined minus a water, RCOR, often made by reacting an acid chloride with a carboxylate. An ester is like an acid plus an alcohol minus water, RCOH plus ROH plus OH2O, the Fischer esterification. And an amide is like an acid plus an amine minus water, though direct combination is difficult. Usually you go through an acid chloride or use coupling agents. But conceptually, RCOH plus H2 and RNHR plus H2O. Nitriles are a bit of a special case in that they are synthesized usually from other routes, like dehydration of amides or substitution of cyanide on alkyl halides, but they too can yield carboxylic acids through hydrolysis, so we consider them related. What's fascinating is that all these derivatives can interconvert through a common mechanism, nucleophilic acyl substitution. The carbonyl carbon in carboxylic acid and its derivatives is electrophilic. It has a partial positive charge because the electronegative atoms O, Cl, etc. are pulling electrons away. Additionally, the presence of a potential leaving group, Cl, amines, OR amines, etc., attached to that carbon means if a nucleophile attacks the carbonyl, the molecule can kick out the leaving group and restore the carbonyl. This is in contrast to something like a ketone or aldehyde, which, when a nucleophile attacks, has no good leaving group aside from H-manimines or C-mannans, which are not leaving groups. So they typically undergo addition rather than substitution. But carboxylic derivatives undergo substitution at the acyl carbon. A nucleophile adds to the carbonyl, forming a tetrahedral intermediate, and then the best leaving group departs, regenerating a carbonyl. For instance, if we have an acyl chloride RCOCl and water attacks it, we get a tetrahedral intermediate, then Cl- leaves. The result is RCOOH, the carboxylic acids, now paired with a proton from water forming HCl. So acyl chloride plus H2O, acid plus HCl. If an alcohol attacks an acyl chloride, you get an ester and HCl. If an amine attacks, you get an amide and HCl, which usually gets neutralized by adding an extra base. In general, the more reactive derivatives like acid chlorides and anhydrides can be converted into less reactive ones, esters, amides, by nucleophilic attack and substitution. The reverse, less reactive to more reactive, is not easy. You typically need to use special reagents like turning a carboxylate into an acid chloride with Cl2 as mentioned, because you can't just pull off a OH and replace it with Cl without an activating agent. Let's take a peaceful tour through their relative reactivities. Acid chlorides are the most reactive of the common derivatives. The carbonyl carbon in an acyl chloride is strongly electron poor due to the strong inductive effect of chlorine. Chlorine withdraws electron density. At the same time, chlorine is a weak electron donor by resonance. It does not give much electron density into the carbonyl. So the carbonyl carbon in RCOCl is very electrophilic. It's craving electrons, and Cl- is also a very good leaving group when the tetrahedral intermediate forms. So acyl chlorides react readily with all sorts of nucleophiles, often vigorously. They even react with water in the air, hence often pungent fumes of HCl when an chloride bottle is open. On the opposite end, amides HCl on HR are the least reactive. In an amide, the nitrogen, although it is electronegative, has lone pair electrons that delocalize by resonance into the carbonyl. Nitrogen's lone pair overlaps with the CO-pi system. This means the carbonyl carbon is less electrophilic because the electron donation from N gives the carbonyl a partial negative character, reducing its positive character. Also, MyNH2 or NHR are not great leaving groups. They are basic and you'd have to expel an amide ion, which is not favorable unless forced. So amides are quite stable. You need strong reagents or harsh conditions to hydrolyze or otherwise react them, e.g. prolonged heating in strong acid or base to hydrolyze an amide. Esters, R-CoR, and anhydrides, RCOO-CoR, fall in between. Anhydrides are quite reactive, just a step below acyl chlorides, because the leaving group is a carboxylate, which is stabilized by resonance, and the inductive effect from the acyloxy, AzOCOR group, isn't as strong as Cl, but still the whole structure can delocalize charge. Esters are less reactive than anhydrides. Their MASH or leaving group is not as good as a chloride, but in the presence of acid or base catalysis, esters can be hydrolyzed or converted to other derivatives. We can gently summarize acid chlorides, anhydrides, esters, carboxylic acids, amides in terms of reactivity, roughly. And nitriles, which become amides then acids on hydrolysis, are also relatively less reactive and less strongly activated. Because of these differences, we have a sort of hierarchy. A more reactive acyl compound can be converted to a less reactive one easily, but not the other way around, except by using special tricks. For example, we can start with an acid chloride and react it with pretty much any nucleophile to get various products, with water to get the acid, with an alcohol to get an ester, with ammonia or amines to get amides. An anhydride likewise can react with alcohols to give esters or with amines to give amides, etc. But if we start with an ester to go to an amide or to another ester, transesterification, we often need heat or a catalyst, and to go from an ester or amide uphill to an anhydride or acid chloride, we can't just do it directly. We have to add energy or reagents like converting the acid to acid chloride with Cl2 or converting an amide to a nitrile by dehydration, etc. One common reaction of carboxylic acids themselves is the Fischer esterification, a lovely equilibrium process where a carboxylic acid and an alcohol react in the presence of a little acid catalyst to form an ester and water. For instance, acetic acid and ethanol with a bit of sulfuric acid will slowly form ethyl acetate, an ester and water. Because it's an equilibrium, removing the water, for example by distillation, can drive the reaction to completion. This reaction is essentially nucleophilic acyl substitution under acidic conditions. The alcohol's oxygen attacks the protonated carbonyl, etc., eventually leading to the noise-OH of the acid leaving as water. It's a nice example of how derivatives interconvert: acids, alcohol, ester plus water. The reverse reaction is ester hydrolysis, which under acidic conditions simply retraces the steps. Adding water to an ester yields the acid and alcohol, which is exactly the reverse of Fischer. Under basic conditions, ester hydrolysis, saponification, goes to completion by deprotonating the acid product to carboxylate, making it effectively irreversible. That's how soap is made. Triglyceride esters in fats are hydrolyzed with NaOH, yielding glycerol and fatty acid sodium salt soap. But in our gentle narrative, Imagine each derivative as a slightly different form of the same theme, the carbonyl plus leaving group theme. And by swapping nucleophiles, they can transform from one to another, provided the one we start with is reactive enough to go to the one we want. We have now quietly visited the realms of alcohols and carboxylic acids and their derivative cousins. Let's take a deep, slow breath and transition to a different kind of topic. How do chemists actually know what molecules look like? One key method is spectroscopy, and in particular NMR spectroscopy, nuclear magnetic resonance. Don't worry, we'll keep this soft and intuitive. NMR is like listening to the whispers of atomic nuclei in a magnetic field. The basic idea is that many atomic nuclei, like the hydrogen-1 nucleus, which is just a proton, and carbon-13, behave like tiny spinning magnets. Normally, these little nuclear magnets are randomly oriented, but when we place them in a strong external magnetic field, let's imagine gently lowering our sample into a powerful magnet, a common step in NMR experiments, the nuclear magnets tend to align with the external field, much like compass needles aligning with Earth's field. Specifically, they have two possible states: aligned with lower energy or against higher energy, the field, for a spin-a-half nucleus like a proton. Now, if we irradiate these nuclei with just the right frequency of radio waves, we can make them flip from the lower energy alignment to the higher energy one by absorbing energy. When they relax back down, they emit signals. NMR spectroscopy is essentially about detecting those signals and translating them into information about the molecular structure. For hydrogen H NMR, often just called proton NMR, each chemically unique hydrogen in a molecule gives rise to a signal at a certain frequency or field strength. The exact frequency is reported in a standardized way as a chemical shift in parts per million, ppm. This chemical shift is like a fingerprint that tells us about the electronic environment of that proton. If a proton is in an electron-rich environment, the electrons shield it from the external magnetic field somewhat. They create a little opposing local field, diamagnetism, that reduces the net field felt at the nucleus. Because it's shielded, it takes a slightly lower frequency energy to flip its spin. We say such a proton resonates upfield at a lower ppm value. On the other hand, if a proton is near electron withdrawing groups, or in an environment where electrons are pulled away, it is deshielded. It feels more of the external field, so it needs a higher frequency to flip. Such a proton resonates downfield at a higher ppm. As an example, consider a simple alkane proton, say the hydrogens in methane or ethane. They are surrounded by electron-rich CH bonds and not near any highly electronegative atoms or pi systems, so they are fairly shielded. They tend to appear at around 0.5 to 2 ppm in the NMR spectrum. In contrast, an aromatic proton, a hydrogen directly on a benzene ring, is in a very electron-poor situation because the ring's circulating pi electrons induce a magnetic field that actually deshields the hydrogen. Aromatic protons typically show up around 7 to 8 ppm, much further downfield. If a proton is on a carbon next to an electronegative atom like chlorine or oxygen, for example CH3CH2O something, it will appear somewhere in the middle, often around 3 to 4 ppm, because the electronegative atom pulls electron density away, deshielding the proton moderately. The NMR chemical shift thus gives a clue. A signal around 1 ppm might be a methyl group in a plain alkane environment. One at 9 to 10 ppm suggests an aldehydic H very deshielded by the C equals O. One at 11 to 12 ppm is likely a carboxylic acids OH, extremely deshielded by both the C equals O and the OH bond's polarity, and so on. The spectrometer in practice uses a reference compound like TMS, tetramethylsilane, defined as ppm, and measures each proton's frequency relative to that. But in our calm journey, it suffices to know chemical shift tells us the electronic environment of the proton, whether it's in a crowded electron party or left out in the electron cold. Another piece of information from a proton NMR is the integration or area under each signal, which corresponds to the number of protons contributing to that signal. The spectrometer can be used to measure how big each signal is, often shown as a step in an integration trace or simply reported as a ratio. For example, you might see that a certain signal is 3 times the area of another signal, indicating it comes from 3 identical protons versus 1 proton for the smaller signal. If we had ethanol as a sample, the CH3 group's protons, 3 of them would give one signal with triple the area of the CH2 group's signal, which has 2 protons, and the OH, 1 proton, might be a separate, smaller signal, though sometimes OH can be tricky due to exchange, but let's keep it simple. Integration thus answers the question, how many hydrogens produce this signal? In a well-calibrated NMR, the integrals areas of the signals are proportional to the number of equivalent protons responsible. Perhaps the most charming feature of proton NMR, though, is the splitting or multiplicity of signals. Instead of appearing as one single peak, a proton signal might be split into 2, 3, 4, or more subpeaks. This splitting is caused by spin-spin coupling. Basically, neighboring non-equivalent protons act like little magnets that influence each other's energy levels. If a proton has an adjacent proton on the next carbon over, typically, the neighbour's spin can be either up or down, which slightly changes the field felt by the first proton. So the first proton signal is split into 2, a doublet, 1 peak for the neighbour's spin up, 1 for spin down. If a proton has 2 neighbours, and if those 2 are equivalent to each other and couple equally, then there are more combinations. Both neighbours could be up, 1 down, or both down. That splits the signal into 3 peaks, a triplet. 3 neighbours would split it into a quartet, 4 peaks, and so on. This is often summarised as the n+1 rule. A proton with n equivalent neighbouring protons will be split into n+1 peaks. The pattern of the splitting, like the relative intensities of those subpeaks, usually follows Pascal's triangle. For example, a triplet has a 1-1-2-1 intensity pattern. The distance between the subpeaks of a split signal is called the coupling constant J in Hertz, and it reflects how strongly the spins influence each other. But for our dreamy overview, the key is multiplicity, reveals the number of neighbouring protons. So if you see a triplet and a quartet in an NMR, and the integration of the triplet corresponds to 3H and the quartet corresponds to 2H, you might deduce you have a -CH2 -CH3 group. The CH2 sees 3 neighbours, so it's a quartet. The CH3 sees 2 neighbours, so it's a triplet. 3H versus 2H areas match a CH3 and CH2. This is exactly the pattern for ethanol's CH3-CH2 group in many cases. As another example, imagine a amides CHH32, an isopropyl group. The central CH has 6 equivalent neighbours, the 6 hydrogens of the 2 CH3 groups, so it would appear as a septet split into 7 since n+1 equals 6 + 1. Each of the CH3 groups sees 1 neighbour, the CH, so each CH3 gives a doublet, split by the single adjacent proton. Indeed, isopropyl groups often show a doublet, integrating to 6H, and a septet, integrating to 1H, a telltale sign. We softly see how splitting patterns give us a connectivity clue. They tell us how many hydrogens are next door to each proton. Putting it all together, a proton NMR spectrum provides a set of signals, each with a chemical shift, environment info, an integration, how many H, and a multiplicity neighbour info. By analysing all these features, a chemist can piece together the puzzle of a molecule's structure. It's like hearing a chord of music and picking out the individual notes and instruments. Each NMR signal is a note telling you something about one part of the molecule. With some practice, you can recognise patterns, like the ethyl pattern of triplet quartet, isopropyls doublet septet, aromatic multiplets, etc., and deduce which pieces connect to which. Now, in addition to HNMR, there's 1pCNMR, NMR of the carbon-13 isotope. Carbon-13 is much less abundant, about 1% of carbon atoms are 1pC, since most is 1pC, which has no magnetic spin, and inherently it gives weaker signals, so 1pCNMR is typically done in a way to get just the basic information. In a 1pCNMR spectrum, each distinct carbon atom in a molecule gives a separate signal, assuming they are in different environments. Symmetry can make multiple carbons equivalent and give one signal. The chemical shift range for an OFC is much broader, roughly 0 to 200 plus ppm from TMS. The scale is such that carbons in different functional groups fall in different regions. For instance, sp-Qua alkane carbons usually show up in the 0 to 50 ppm range, with more substituted ones a bit downfield, 20 to 50 ppm. Carbons attached to electronegative atoms or in certain functional groups might be 50 to 100 ppm. Aromatic alk and alkene carbons tend to be around 150 ppm, and carbonyl carbons, like in acids, esters, ketones, are often way downfield, 160 to 220 ppm. In routine TRPC NMR, we generally do broadband proton decoupling, which means we remove the splitting effects between carbons and attached hydrogens. This is done to simplify the spectrum and increase signal strength. As a result, nearly all WIMP-C signals typically appear as single unsplit peak singlets. We also don't usually integrate WIMP-C signals for quantitative proton counts because the technique isn't as uniformly sensitive for different carbons. Some carbons naturally give weaker signals depending on various factors like relaxation times. So, we mainly use Guncan-C NMR to tell how many distinct carbons are present by counting signals, and sometimes to infer what types they are from chemical shift. For example, if I see a C spectrum with, say, 5 signals, I know there are 5 unique carbon environments in the molecule. If one of those signals is at 180 ppm, I suspect a carbonyl, likely a carboxylic acid or ester carbonyl. If I see signals around 128 ppm, perhaps that suggests an aromatic ring carbon. A signal at 20 ppm could be a methyl carbon, and one at 70 ppm might be a carbon attached to an oxygen, like an alcohol or ether carbon. And if I saw only 2 signals, one at 30 ppm and one at 172 ppm, and I knew the formula was C2H4O2, I might deduce I have acetic acid, CH3COH. One carbon is the methyl 30 ppm, one is the carbonyl 172 ppm. Thus, IUPAC NMR is a nice complementary tool. It gives the carbon skeleton outline, while HNMR fills in the details of hydrogens attached to that skeleton. To summarize this gently, in NMR spectroscopy, we place our molecules in a big magnet and listen to the radio frequency signals from their atomic nuclei. The proton NMR tells us how many types of hydrogens there are by number of signals, what environments they are in by chemical shifts, how many of each by integration, and who their neighbors are by splitting patterns. The carbon-13 NMR tells us how many types of carbons and hints at what kinds by chemical shift range, usually in a simpler spectrum of single peaks since we decouple the H's. By combining these, plus sometimes other spectroscopic data, infrared to see functional groups, mass spectrometry to get molecular weight, etc., though those are beyond our current cozy discussion, an organic chemist can determine the structure of an unknown compound. It's like solving a gentle puzzle. Each piece of data narrows down the possibilities until only one solution fits all the clues. In fact, solving NMR puzzles is a common exercise in organic chemistry courses. You use all the spectroscopic hints to propose the correct molecule. It's quite satisfying, almost like a form of molecular detective work, but one can do it calmly and systematically. As we near the end of our journey, let's softly recap and reinforce some of the major points we've covered in this meditative exploration. We met the alcohols, characterized by the iso-H group, and saw how they can form hydrogen bonds, leading to high boiling points and water solubility in smaller members. We classified alcohols as primary, secondary, or tertiary, depending on substitution, and discussed how to name them with the -ol ending. We observed that alcohols are only weakly acidic, requiring strong bases to form alkoxides, and they can act as weak bases themselves by accepting protons. We then described gentle ways to synthesize alcohols by substituting alkyl halides, by hydrating alkenes, and importantly by reducing carbonyl compounds with hydride donors like NABH-GOR and LALH-GOR. The reduction of an aldehyde gives a primary alcohol, of a ketone a secondary alcohol. We marveled at the Grignard reagent, how an organomagnesium halide, essentially R-menins in disguise, can attack carbonyls to build new CC bonds and form alcohols after water is added. We saw that Grignards add to formaldehyde to give primary alcohols, to other aldehydes to give secondary, and to ketones to give tertiary alcohols. And we remembered to keep Grignard reagents away from water, lest they be quenched into hydrocarbons. Next, we turned the coin to oxidation, noting that primary alcohols can oxidize to aldehydes and onto carboxylic acids, secondary to ketones, and tertiary not at all under normal conditions. Strong oxidants like chromic acid could take a primary alcohol all the way to an acid, whereas milder ones like PCC stop at the aldehyde. We then entered the world of carboxylic acids, seeing them as polar, strongly hydrogen-bonded molecules, often forming dimers, with relatively high boiling points and melting points. We learned that their acidity, pKa-5, comes from the resonance-stabilized carboxylate ion, making them much stronger acids than alcohols, but still weak compared to mineral acids. We acknowledged that carboxylic acids can be made by oxidizing primary alcohols or alkyl benzenes, by hydrolyzing nitriles, or by the elegant Grignard plus CO2 route. The derivatives of carboxylic acids expanded our view. We have acyl chlorides, anhydrides, esters, amides, and nitriles, all different masks of the carboxyl group. We softly compared their reactivities, noting acyl chlorides are very reactive, thanks to strong induction and a great leaving group, while amides are very sluggish due to resonance donation from N and a poor leaving group. We learned that they all undergo nucleophilic acyl substitution, where a nucleophile adds to the carbonyl and then a leaving group departs, reforming the carbonyl. This mechanism allows interconversion, e.g. acid chloride to ester, ester to amide, etc., by exchanging the leaving group. We also noted that one can go down the reactivity ladder easily, more reactive to less, but to go up, like acid to acid chloride, one needs special reagents like OCl2. We briefly touched on Fischer esterification, combining an acid and alcohol to get an ester in acidic conditions, as a gentle equilibrium reaction, and its reverse, hydrolysis of esters. Through all this, we kept our tone soft and unhurried, reinforcing that all these functional groups and reactions are part of a connected web of organic transformations. Finally, we tuned into the sounds of NMR spectroscopy, treating it as a friendly tool that lets us listen to the nuclei. We established that each unique hydrogen gives a signal, and its chemical shift tells us about shielding versus deshielding electronic environment. We saw examples like alkane H around 1 ppm and aromatic H around 7 to 8 ppm, illustrating how environment shifts the resonance. We discussed splitting patterns, how neighboring hydrogens split a signal into doublets, triplets, etc., revealing how many neighbors a proton has. And we mentioned integration, the idea that the area of each proton NMR signal is proportional to the number of hydrogens of that type. We then described a small C NMR in a gentle way. Each carbon gives a single peak with proton decoupling, and the chemical shift indicates the type of carbon, with a broad range where carbonyls are far downfield, etc. By combining proton and carbon NMR, one can deduce a molecule's structure, truly allowing the molecule to tell us its story through these spectral clues. Our organic chemistry journey in this session has been calm and comprehensive. We wandered from functional group to functional group like a traveller moving through a peaceful landscape, observing the features of each terrain. We gently repeated important points, not to overwhelm, but to let them settle in your mind like leaves floating down to a quiet pond. As you drift closer to sleep, you might not remember every detail we talked about, and that's perfectly all right. Even in sleep, your mind might retain some general feelings and understanding that alcohols have an OH group and can hydrogen bond, that carboxylic acids are a bit stronger as acids due to resonance, that NMR is a friendly voice of the atoms. If you're still awake enough to recall, think softly of an alcohol molecule, say ethanol, and how its OH group allows it to mix with water and form hydrogen bonds with its neighbours. Think of a carboxylic acid like acetic acid, how it can give a proton away to become acetate, sharing the negative charge between two oxygens. Envision a Grignard reagent forging a new bond, turning a ketone into a tertiary alcohol, and how careful one must be to keep water out until the right moment. Recall that an oxidation of a secondary alcohol is like letting it breathe out H2 and form a ketone, whereas a tertiary alcohol just doesn't have that breath to give. And imagine the NMR spectrum of a simple molecule, perhaps the triplet and quartet of an ethyl group, as a little musical harmony, the triplet 3 peaks telling you, I have 2 neighbours, and the quartet responding, I have 3, a gentle conversation in the language of spectroscopy. Organic chemistry at its heart is a story of how atoms bond and transform. Tonight we've heard part of that story in a slow, soothing manner. You don't need to memorise or analyse it right now. You can let it wash over you, knowing that your mind is absorbing patterns and concepts even as you relax. Perhaps you're already halfway to dreaming, where molecules might dance in new shapes behind your closed eyes, presenting what you learned in creative, subconscious ways. If so, that's wonderful. You're learning and resting at the same time. As we wrap up, let all these concepts settle down. We covered a lot, but in a meandering, gentle fashion. You can imagine putting each topic, alcohol properties, Grignard reactions, NMR signals, into a safe little box for the night, knowing you can open them again later when you need them. For now, it's time to let go of the waking world of molecules and drift fully into the soft realm of sleep. Feel free to release any remaining thoughts and simply float, with their assurance that the knowledge will be there in your mind when you need it, slowly strengthened by this relaxed exposure. You did very well just listening quietly. Now the chemical characters bid you good night. The ethanol and acetic acid wave gently. The Grignard reagent gives a tiny salute. Careful, not near water, and the NMR lullaby fades out. Your mind can rest, consolidating what you've heard into understanding without any effort from you. Breathe softly. Let your body be heavy and comfortable. The world of organic chemistry will be here in the morning or whenever you return, but for now, you've earned a deep and peaceful sleep. Sweet dreams and good night.